Hi, this is Jose Luis, and welcome to a new hands-on exercise on the series Introduction to Parametric Modeling. In this one, what we're going to try to do is replicate an architectural landmark, the Jewish Holocaust Memorial by Peter Eisenman in Berlin. It looks something like this, and the way we're going to do that is that we're just going to create a very simple definition that starts from a surface representing the undulation of the blocks, and then we're just going to perform a series of operations so that we end up with each one of those blocks. And imagining that we're going to be the designers. Because it's going to be parametric, then we will be able to control how many blocks we have in each direction. We will be able to control the size of the blocks in each direction as well. And we will also be able to control the input surface, so that if I just modify the surface like this or like this, then the shape of the blocks adapts dynamically. This could be a really interesting exercise because it showcases the power of parametric modeling in the case of when you design your whole parametric set of relationships, then doing quick iterations about how different versions of more blocks, less blocks, more width, less width, how this could affect your design and help you reach, for example, different iterations of design so that you could decide which one looks better, which one looks worse, and which one is going to go the one that is going to be the one that goes to the competition, the one you sell to your client, etc., etc., and help you make design decisions. So this exercise that we're doing in this video is going to be an oversimplified version of the actual original monument, because I want to use it as an introductory exercise in the Introduction to Parametric Modeling series that I'm working on right now. So this is catered specifically for people who are beginning and are still learning the basics of algorithmic modeling. If you are interested in a more comprehensive, detailed version of this exercise, or if you feel you are at a more advanced level, I highly recommend that you check the exercises that we did previously on our algorithmic modeling challenge. And actually, fun fact, these three, the algorithmic modeling, the Berlin Holocaust Memorial, were the very, very first videos that we recorded in this channel in Parametric Camp. But these three videos are a basic version. Then version 2 is a more advanced, very detailed version with many of the original details in the monument. And the third one is the same as the second one, but implemented in C#, in purely scripting, if you are interested in those kind of things. Okay, so let's take a look at how can we implement this, a simple version of this exercise in with parametric modeling inside of Rhino and Grasshopper. Let's take a look at that. All right, let's do this. So just a quick reminder that this version of this exercise that I'm going to do is oversimplified and it's taking tons of shortcuts. If you want to see a more in-depth, more systematic approximation to the original monument, please make sure that you check the algorithmic modeling challenge that I referenced in the introduction, okay? But for this one, because I just want to do something really easy, like a really quick prototype, the way I'm going to approach this exercise is going to be the following. I would like to start with a surface in 3D. I'm going to imagine that I am the person who is designing this monument and that I want to have some kind of, I want to use this tool as a way for me to find what is the really nice shape of the blocks and the curvature, etc., etc. So that's why I would like to start as an actual surface in Rhino as the input parameters, because I will want to play. Once I have the design ready, all the algorithm ready, I will want to play with the control points and drag things around, etc., to play with the geometry of the surface and find the ideal shape for the blocks, etc., etc. So that's what I'm going to use as my design tool. And then the process that I'm going to follow to generate the blocks for this monument is going to be as follows. What I'm going to do is I'm going to take that surface and I'm going to subdivide the surface into a grid of points. That grid of points is going to be at regular intervals in the U direction of the surface and in the V direction of the surface. If you remember from previous videos, we talked about how surfaces, nerve surfaces, have an internal have two internal directions, and we can subdivide them into equal parameter lengths. Then, once I have all those points in 3D space, I can do a very simple operation of taking all those points that will have x, y, and z coordinates, and then projecting them down to the ground, if you will, by basically taking all those points, deconstructing them, and creating new points with the same x and y, but with the z height being all at the same level. So for example, the value of 0. If I do that, then I will get basically a copy of all the points that I had on the surface, but projected to the ground, because all their z coordinates are going to be 0. Once I have all those points down in the bottom, then it's going to be super easy to just basically create some kind of primitive shape. So for example, a rectangle on top of each one of those circles, centered on top of each one of those circles. The rectangle will be the footprint of the block, and that the dimensions of which I can control parametrically. I can have sliders, the width and the height of the block. And then after that, I will want to extrude each one of these blocks in a way that it creates a cube, but each one of the heights of these blocks will have a different height, and it will have a different height that will correspond to where it was on the three-dimensional space. So what I can do is I can actually extrude each one of them with the direction of how high it was in the z axis. That will give me, I can calculate all of that. It's numbers that I will have as part of my parametric definition, and then I can then extrude each one of them into different blocks, giving me something like this. I apologize for the quality of the drawing, but you know me. I am not much of a sketcher. No, Martinez Alonso would do a much better job than I have done here, but you get the point. Each one of the blocks will go higher or lower depending on how far it was, how far the base was from the surface, and therefore all the blocks will end up recreating that curvature of the original surface. All right, so I think these are the steps that I'm going to follow to do this exercise. It's going to be actually super simple, but again, if you want a more in-depth, more detailed, and more faithful exercise, faithful to the original monument, make sure to check the algorithmic modeling challenge for the Berlin Holocaust Memorial. So let's do a quick prototype following these steps inside of Grasshopper, in our case. Let's start from the beginning. I'm going to have my Rhino here, my Grasshopper, and then the first thing I would like to do is to create the surface that is going to be the input to my monument. So I'm going to use the technique. I'm just going to go to the right view of the screen, and then here I'm just going to create a curve in 3D space, like something like this, for example, and then I'm going to create another one, and I'm going to snap the ends so that it's more or less square in the footprint. So what I'm going to do is I'm going to start from the same point, but now perhaps the curvature, if you will, is going to be a little more pronounced. All right, but they both start and end on the same place. I'm going to go back to perspective, and then I'm going to move this curve in the y direction to create a surface that is more or less square. Not really, but it doesn't really matter. And then what I'm going to do is I'm going to type loft, and then I'm going to loft this curve and this curve together. And therefore, I will be creating this kind of surface in 3D. If I right click here and I type and I go for ghosted, I can see this other representation that is a bit more. And you can see that I still have the curves that I'm going to delete, I have the other curve that I want to delete. And if I click on my surface and I press F10, the control points of my surface show up. And then potentially in the future, I will be able to play with those control points to modify the surface of the curvature and make it more bulgy, less bulgy, etc., etc. But I will do that perhaps by the end. So maybe in the meantime, I'm going to do this. Yes, so that I can have something like that. All right, I'm going to call this my design surface, because again, it's going to be the one that is going to be driving the shape of my monument. And I'm going to bring that into Grasshopper by creating an empty surface parameter box. So that's going to be surface here. I forgot to put some bifocals here. For those of you who are still not using icons, please switch to icons. Trust me, it will be good in the long run for you. And then I'm going to right click here, set one surface, and now I have my surface here. And I'm going to drop a panel, which I'm going to be using to keep track of things. Now the next thing that I want to do is, if you remember, I want to subdivide my surface into a grid of UV points. The way I can do that is by going to surfaces and going to utilities, and here I can see a component that is divide surface and surface frames. So the divide surface generates a grid of UV points on a surface. This is very interesting. I can see that the input is the top of the surface that I want to subdivide, and U and V are the number of segments in each one of the directions. So I'm going to plug here the component, and you can see that immediately I get UV subdivisions, and then I'm going to drop here, for example, I'm going to type 20 so that that's a little too much. I'm going to type here 10 so that I have control about how many subdivisions I have in each direction. So 10 and 10, and therefore I can now control this. All right. Just a quick note, if you remember from where we were talking about surfaces, I remember how I was telling you that UV, that the parameter space in a curve and in a surface may not be equally distributed. So you can see very clearly here in the top view how the parameter space is more dense here and is less dense here, which means that the distribution is not going to be perfectly orthogonal, perfectly perpendicular on plan view. This is also very clear to see here how the curvature here, because of the distribution of the control point, you can see that the control points are closer here and they're more distributed farther apart. That's why there is a larger distance here and here, but the points in this area, for example, are more concentrated. So this is just to say that UV subdivision will not give you points that are equally distant in Euclidean space. They are equally distant in internal UV distance, but that may not have a constant rhythm in Euclidean world coordinates. Okay? So that's why I was saying before that this is a little bit of a shortcut, because in the original monument, the blocks are actually distributed orthogonally in a grid, which is not going to be the case here. But anyway, just an approximation. Wonderful. So now we can play with how many blocks we have in each direction. And then we can see that the outputs of this component are the points that we are getting. So that's going to be all these points here. And we are going to see very soon why there is like these categories here and why they are subdivided in kind of groups. We'll see that very soon in the next coming videos. And you can also see that the outputs are the normal vectors to the surface on those points and where those points are in the UV space. So in coordinates 0, 0, 0, 7, 0, 14 in each one of those directions internally. So but these are the X, Y, Z coordinates in world space. So the next thing that we wanted to do was to project those points to the ground. And what we were going to do about that is just basically take all those points, take the X, Y coordinates and create new points at 0, Z with the same X, Y, Z, with the same X, Y. So let's just do that. I can take all those points, and then what I'm going to do is with vector point deconstruct, I'm going to extract the X and the Y. For example, these are all the X's, these are all the Y coordinates of each one of those points. And then I'm going to create a new family of points that is going to take the same X, the same Y, but Z is going to be 0, which is the default that we have here. So you can see now how I have created here a new family of points. If I compare this, I have the same points, but if I compare this with what I have right here, you can see that I have the exact same points with the exact same X and Y, but Z is now 0. So this is all the points here at the bottom. Wonderful. We are very close to done. So now what is the next thing that we want to do? Well, if you remember, the next thing that we want to do is now we just want to draw the footprint of our blocks. So how are we going to do that? Again, we're just going to find, for example, a rectangle component. The rectangle component is going to be somewhere in curves, and it's going to be under here, rectangle. And then I can place rectangles that are going to be, the base plane is going to be P, and then X and Y are going to be the dimensions of the rectangle in the X and Y directions. So this is going to be here, and then I'm going to set here values for the width of the block. So that's going to be, for example, let's say there's going to be a slider with 10 units and another slider with 10 units. One is going to be X and the other one is going to be Y. And these are super big, so I'm just going to make them much smaller. All right. And you will notice that the rectangles that I am drawing are drawn from the corner. So the point is the coordinates of the corner. This is because the rectangle component takes X and Y. It doesn't take a number. It takes a domain, which is a range between two numbers. And because I'm just giving it one number, basically it does from 0 to that number. And that's why the rectangle is offset to one side from this point. Is there any way that I can generate a simple center rectangle without getting into domains, which I want to get later on in these videos? Let me take a quick look. So I couldn't find one, so I wonder if I can just explain domains real quick. So let me go back to the problem. The problem is that this rectangle component, for the dimensions in the X and the Y, you can see that the hex icon is indicating us that is this thing that is like a bar with two ends. If I look at my my primitives, you can see that this is what's called a domain. And a domain is just basically a range of between two numbers. So instead of saying 4, you say from 0 to 4 or from -4 to 4. So the idea is that this is asking for a domain so that it knows how to center the rectangle in each one of the directions. And because I'm giving it just one number, not a domain, it converts that automatically to a range, a domain that goes from 0 to the number that I gave it. So if I want to actually center my rectangle on top of that point, what I will need to do is basically I will need to create a domain that instead of going from 0 to the width of the box, what I would need to do is to create a domain that goes from -half of the width to +half of the width. So the way I'm going to do that is, first of all, I'm going to create a domain by going to the Math tab and going to the Domain category. And here you can see that you can construct a numerical domain with the two ends, given the two ends. So I'm going to create one here. A is going to be the start of the domain and B is going to be the end of the domain. So what I'm going to do is I'm going to type here expression component. That is going to be whatever you'd say, give me -x divided by 2, whatever you give me. And then I'm going to plug that in here, and then I'm going to copy paste a new one, which is going to be the same but in positive. So that's going to be, now if I plug my panel here, you're going to see that from 1.5 whatever, or from 2, what I get is a domain that goes from -1 to 1. And let's see if I plug that into X, you can see that now in the X direction, the rectangle is centered. So the only thing that I need to do is I just need to copy and paste this and do that for the Y direction as well. And then feed that into the Y component. And therefore, now my rectangles are perfectly centered on top of the base points on top of the base points. All right. Okay. So that was not very difficult, actually. So domains, again, domains are just basically an interval between two numerical extremes. As simple as that. Now, the last thing that I would like to do is I would like to take all of these boxes and extrude them, or create an actual box that is as high as the C of the original points that were on the surface. So how can I do that? Well, there are many ways that I could do this. I could, for example, take the freeform component and I could extrude. What is extrude? I could extrude this. I could extrude this in with a direction, which could be a vector in the C direction. For example, I could do this, and then I could just do a vector, a C vector that is multiplied by the height of all those points. And then I could have that. The problem is that this will not work great for rendering because the extrusion doesn't cap the ends. So I'm actually going to use a different technique, which is going to be, I'm going to create cubes here under primitives. There's actually one box that is very convenient in this case, which is a box that is defined by a rectangle, which I already have, and by a height, which I also have. So I'm going to place that here, and you can see that the input is the base rectangle. I already have this here. And then the height, instead of being 0 to 10, is going to be 0 to the C height that I have for each one of the points. Remember that each one of the points had a C height, and then therefore now you can see that all these boxes are closed, and that each one of the boxes at the center is actually showing here, and it's tangent. It's not tangent exactly, but it's coincident with that point on the surface. And what's beautiful about this now, as usual, because this is parametric design, because all the relationships are parametrically bound to each other, what I can do is I can modify the original surface. So for example, I can just move it anywhere, and then all the blocks will move correspondingly. I can press F10 to turn on the point cloud, and then decide, I want this point to be much higher. Whoa, so I'm going to create a larger bulge here. What other points? So for example, I want this point, or this point here, I want it much lower. So I want to create like some kind of curvature there. So you can see that now I have some curvature here. This point is also going to go down. So I'm just going to decrease this, and maybe I went too far with this one. And then you can start iterating and you can start refining the overall shape. I can actually hide this. I can just click it and type hide in Rhino, and then this will hide it. And then whenever I think I'm ready, I can just go ahead and go to the boxes and right click, type bake. I'm going to group them so that I can move them together as a group. All right. And now I have my geometry inside of Rhino, which I can move. And then, for example, if I choose right click, render, I can do this like ambient occlusion kind of representation, and I can see what the boxes would look like as a monument, for example. And I could now send this to my colleagues, to the competition. I could do some renderings. I could do whatever I wanted with this right now. So hooray! This is parametric modeling. And this is a bit more of an interesting example of the things that we can do with algorithmic modeling by just simply creating the chain of relationships that define a particular geometry. And again, I can keep iterating here. I didn't touch this, but I can say I want the blocks to be a little smaller, but I actually want to have many more of them in every direction. Now I'm going to make them a little tighter, a little blah, blah, blah. Ooh, they're overlapping here, etc., etc. You see, I can work. Let me bake this one. So I'm going to bake them, and then they show up here, and now I can compare it to my previous iteration, and I can see them back to back and be like, this one is too big, this one is like more. So I can make design decisions and really iterate real quick over different versions of my geometry, which is Again, like one of the fundamental powers of parametric modeling. Once you have established the relations between all the geometry entities, then iterating and seeing different versions and different examples becomes as simple as just changing some sliders or pulling up and down the surface, the input surface. So I think this is where I wanted to end today. So hooray! This was the Berlin Jewish Holocaust Memorial Museum by Peter Eisenman. Is that it? Is that what we're doing? Yes, I think I'm going to wrap it up. Thank you very much. If you like this video, please consider subscribing to the channel, liking the video, turning on notifications. And also remember, if you want to see a more advanced version of this exercise with more details, more in depth, and much more faithful to the original monument by Peter Eisenman, make sure to check the algorithmic modeling challenge that we did, which should be popping somewhere here, somewhere on the screen. And make sure that you do that. And also, if you're interested in C#, we actually did this typing it in pure code in a C# script component in Grasshopper. So it could also be interesting if you are at a more advanced level in learning how to do these things yourself. Okay? Thank you very much. And let's move on into the Introduction to Parametric Modeling series. And let's keep learning more stuff to make even better and cooler things. Thank you very much. See you on the next video.